Welcome to the deep dive. Today we're tackling big O notation.
That's right.
Think of it as understanding the speed limits hidden inside technology.
Yeah, how things scale.
Our mission today, to help you get the core ideas of algorithm efficiency, how performance changes as data piles up, but without needing a computer science degree.
Exactly. Keep it accessible.
We're using 10 key questions as our map for this. And honestly, knowing this stuff is almost like having a superpower.
Huh. In a way.
It helps you figure out if some tech will crawl or fly when things get busy.
It really does. So Big O, basically it describes an algorithm's performance could be time, could be memory usage, or space as the input size grows.
So not just how fast it is right now, but how its speed changes.
Precisely. It's key for comparing different ways to solve a problem and crucially predicting how they'll cope with, well, massive amounts of data.
Okay. So how does Big O actually measure efficiency then? It's not like timing it with a phone, right?
No, not at all. Big O looks at the dominant factor, the thing that impacts performance the most as the input gets really big.
Mm-hmm.
Think about finding a contact on your phone. You could just scroll and scroll.
Yeah, if you have tons of contacts.
Right. Or you could use the search bar. Big O helps us describe how the time needed for each method changes as you add more and more contacts. It kind of ignores the small, constant stuff.
Like how fast you can physically tap.
Exactly. Or the fraction of a second it takes to open the app. It cares about the trend as the number of contacts in grows large.
Got it. So what are some common patterns? How does performance typically scale?
Well, a great one is O1, or constant time.
Constant, meaning it doesn't matter how much data.
Pretty much. Imagine if you knew the exact memory spot for a contact. Boom, you
Wow.
get it instantly. Doesn't matter if you have 10 contacts or 10 million.
Nice. What's next?
Then you've got ON, that's linear time. This is like that scrolling example.
Okay. Double the contacts, roughly double the scrolling time.
You got it. The time taken grows directly in proportion to the number of items.
And I guess it can get worse than that. You mentioned ON.
Oh yeah, ON quadratic time. Imagine comparing every single contact in your phone to every other contact.
Oof. Why would you do that?
Maybe finding duplicate contacts in a naive way gets really slow really fast as your list grows.
Okay, definitely want to avoid that. Is there better stuff than linear?
Absolutely. A really good one is O log n, logarithmic time.
Logarithmic, like in math class.
Kind of. Think of using that search bar again. Each letter you type dramatically cuts down the possibilities.
Right, you narrow it down super fast.
Exactly. Even if your contact list gets huge, adding more contacts only makes the search slightly slower. It's very efficient, like finding a word in a dictionary.
A log n sounds like the dream for search features then. Now, you mentioned Big O usually focuses on the worst case. Why is that? Why not the average?
Well, the worst case gives you a guarantee. It's like saying, look, even if everything goes wrong, if the data is arranged in the worst possible way for this algorithm, it won't perform worse than this.
It's about reliability, a performance ceiling.
Exactly. It provides an upper bound, which is often what matters most, when you need to ensure something doesn't just fall over under stress.
Makes sense. And I've heard of other notations, like big theta, big omega. Are they important?
They exist, yeah. Big theta is often used for the average case or when the best and worst case are the same. Big omega A is the best case scenario.
Like finding your contact on the very first try.
Right. But honestly, for practical purposes, especially when talking about how systems handle growth, Big O's focus on that upper limit, the worst case, is generally the most discussed and arguably most useful for planning.
Okay, sticking with Big O then, let's go back to N. That just means the size of the input, right? Like the number of contacts.
Precisely. N represents the size of whatever the algorithm is processing. And how an algorithm reacts to N getting bigger is the whole point.
So an ON algorithm might be fine for 10 items,
Totally fine.
but totally unusable for 10 million.
Absolutely. Imagine a social network trying to suggest friends by comparing every user to every other user that's ON. With millions or billions of users, it's just impossible. It wouldn't work.
Yikes. Okay, what about O2N? Exponential complexity. That sounds even worse.
It is. Exponential is generally really bad.
Right.
With O2N, the work roughly doubles every time you add just one more item to the input in.
Doubles, wow.
Yeah. Think about trying to guess a password by trying every single combination. Each extra character makes the number of possibilities explode exponentially. These algorithms become impractical incredibly quickly, even for seemingly small n.
Okay, avoid exponential at all costs if you can. So question, if one algorithm has a better big O, say ON, and another is ON, does that mean the ON one is always faster in the real world?
Not always, especially for really small inputs. Remember, Big O ignores constant factors and lower order terms.
Ah, the setup time and stuff we mentioned.
Right. An ON algorithm might have a higher initial setup cost than an ON. So for like 5 items, maybe the ON
Yeah.
is quicker. But as N grows, and in computing often grows a lot, the algorithm with the better Big O complexity will eventually, and usually dramatically, outperform the one with the worse complexity. Big O tells you about the scaling trend, the long-term behavior.
So it's a high-level comparison tool focusing on scalability rather than exact milliseconds for small tasks.
Exactly. It lets you compare algorithms conceptually, understand their fundamental efficiency limits without getting bogged down in specific hardware tests or micro-optimizations right away. It helps you choose the right tool for the job, especially if you expect the job to get bigger.
Makes sense. And does this apply just to time or?
Good point. It applies to space complexity too, how much memory an algorithm uses as the input size ungrows.
Ah, so you might have a trade-off.
Sometimes, yes. An algorithm could be super fast, good time complexity, but maybe it needs loads of RAM, bad space complexity, or vice versa. Both are important considerations depending on the constraints you're working with.
Okay, great. So to quickly recap, we've got constant time O1, linear ON, quadratic ON, the efficient logarithmic O log n, and the scary exponential O2n.
Right.
And Big O generally looks at the worst case to give us a performance guarantee as the input size n increases. It's all about comparing how algorithms scale conceptually.
That sums it up pretty well. Big O notation is really a powerful way to think about efficiency and growth in, well, pretty much everything driven by algorithms today.
It definitely makes you think differently about why some apps stay snappy and others bog down.
Yeah, it encourages you to consider what's happening under the hood, how that tech you rely on might perform tomorrow when it has twice as much data to handle.
A very useful perspective. Thanks for breaking that down.
My pleasure.